So let's begin. Okay, welcome all. Welcome to week 8 of this doubt solving session or live interaction session for Matlab based programming lab in chemical engineering. So every Tuesday we meet to solve various chemical engineering related problems through Matlab programming, right? This time I have preponed this class to Saturday, so next Tuesday there won't be any class from my side, right? Uh, Now, in this interaction session class, every Tuesday we meet and solve various problems of chemical engineering through MATLAB programming. We understand different concepts, right? So, just brief about me. I am Bhavesh Moorjani. I have completed my bachelor's from chemical engineering department at MS University Vadodara. After that, I was working at state PSU, and then I joined PhD at IIT Bombay. So in my BTech, I was introduced to this MATLAB based programming, and now in my PhD work also I sometimes use it for various analysis purpose. So the purpose of this interaction session is to get you familiarized with the concept of MATLAB programming and how you can apply it for various chemical engineering problems, right? So till now what we have done is we have solved a system of linear algebraic equations, non-linear equations, ordinary differential equations with initial value problems in the MATLAB. We try to focus on the various numerical methods which are available to solve these problems. Then we also compared our numerical method results with the inbuilt MATLAB commands that are there to solve these problems, right? We have focused on various chemical engineering problems involving this type of equations, be it the fluid flow operation, CSTR plug flow reactor operation, or the distillation or liquid extraction problem, where you solve this system of linear equations, right? So now we will move forward with the one more concept, which is ordinary differential equation, but this time instead of initial values we will know the boundary values, right? So that becomes ordinary differential equation boundary value problems. So today's class will be focused on that aspect only, right? So if you remember, in the last class the final problem that we were solving was about co-current heat exchanger design for a double pipe heat exchanger, where co-current flow is there for the hot and cold fluid. How you how you compute the temperature profile of both the fluid along the along the direction of your pipe, right? And we tried to code that, and at the end I had proposed a question that what happens when you have a instead of co-current, when you have a counter current flow, right? So in that case our problem definition becomes slightly different. So initially the same co-current problem was represented by ODE-IVE problem, right? Where you know the at the inlet. So this is how our problem looks like. So what was given to us, that we had to design a double pipe heat exchanger which has a co-current. So one stream is hot, one stream is cold. Hot stream data was given, cold stream data is given, both inlet temperature for hot and cold stream is given. The exchanger data such as overall heat transfer coefficient, heat transfer area per unit length, total length of the exchanger was given, right? And we had to determine the temperature profile along the length of the exchanger, right? So if you do the general energy balance for this heat exchanger, where you get the rate of heat transfer, which is UA delta T, is equivalent to heat gain or loss by a stream, right? So if I consider the hot stream, MCP delta T of hot stream will be UA into delta TH. The area you can represent, since here we had been given the area in terms of heat transfer area per unit length, so that AL into DZ, right? And then you can compute the profile based on the this ordinary differential equations, which gives you the change in the temperature with respect to Z direction, or the length of the pipe, okay, by this equation. And when you put it this equation for hot and cold fluid, you get these two differential equations. Now here the negative sign is to represent that the temperature of the hot fluid is decreasing as we move along the z direction, right? That's why you have a negative sign. Okay, so that was one aspect. So this were two differential equations. We knew the initial value for both the temperature, right? So we have such kind of a system where you have two differential equations representing your temperature value for hot and cold stream along the z direction. You know the value of your temperature at z equal to 0, right? So this becomes ODE-IVP problem, where based on the initial value, you know the value at z equal to 0, you move ahead in the direction z, and at every step you compute the new value based on the previous information available, right? And you get the profile. But now the question is, if instead of co-current our system becomes counter current, then what we do, right? So before going in that direction, let's just first quickly try to code this co-current problem in the Matlab. I have already done it in the previous class, but before starting and moving ahead with the counter current problem, let's just revise that problem, how we code it in Matlab, and then we can move ahead, right? This is recorded. It's working. Okay. Now here our problem is double pipe heat exchanger, with a co-current flow, right? And what are the data given? So these are the data. You have hot stream data, cold stream data, and the exchanger information. Okay, I'm just copy pasting it from the previous code, so we don't waste we don't put too much time here, right? So this is the given data: hot stream, cold stream, both flow rate for hot and cold stream, their inlet temperature, Cp value is given, and then you have the exchanger property. You have overall heat transfer coefficient, area per length information, and then total length of your heat exchanger, right? Now we have to create ordinary differential equation function which represents our energy balance in the system, right? So for that, if you will focus into this equation, so we have one ODE with respect to temperature, change in the temperature of hot stream with z direction, one ODE in the which is change in the temperature of cold stream with z direction, right? Now so here the UA divided by MCP, that becomes constant, and TH minus TC is a variable, right? So let's find the constant of ODE. So let me call one constant as alpha. Your alpha becomes UA MCP by UA divided by MCP for a hot stream, right? So that is U into area, mind you this is area per length, divided by my M hot into CPH. Okay, now this has a negative sign since the temperature of the hot stream is decreasing. Okay, then you have a beta, which is again same, U into area per length divided by MC into CPC. Okay, OD is to represent our system. Okay, so that OD will be, let's say I'm calling it Y, so that will be function of your Z, and let me call heat exchanger ODE is equal to, that will be function of your Z and Y. First part is your minus, so alpha times TH minus TC, so that is alpha, okay, into, let's call it, so here Y represents TH comma TC, okay, so this becomes your Y, Y1 minus Y2, okay, that is one equation. And then you have beta into again Y1 minus Y2. So this way you have created your ODE function, okay. Now just let me save it. Now the initial guess or initial value of temperature, so you know the Y0 value, that is given as TH in comma your TC in, okay, so this is your initial value. Now using ODE solver to find the solution along the Z direction, okay, so for that you will have to create a Z span which will go from Z equal to 0 to your L, okay, correct. Now what we will do, our solution ZY will be ODE-45, which includes function of, this becomes your function of Z comma Y, your heat exchanger ODEs, then your Z span and initial value Y0, okay, you provide it. Now here once you solve it, the first column of your Y will give you the hot fluid temperature, while the second column will provide you the cold fluid temperature, okay, right. You can just plot it also, plot Z versus TH comma Z versus TC, X label will become your length in meter, you can provide Y label as temperature. Now its unit can be anything, so I think it's in degree centigrade, yes, so degree C, okay, right. Then we want to provide the legends. First will be T underscore H and second is T underscore C. Let's run this. There is some issue. THTC alpha beta. This is Y1, Y2, Z span, Y0. Returns a vector of length 1, but the length of initial condition vector is 2. No, it's giving to, have I forgot? What happened? Yeah, ODEs are correct. Might be some spacing issue. Alpha, beta. Yeah, it's giving me two data only. Why it's not showing? Oh, here. Yeah. No, there was an issue in the notation part. That's why it was giving this error. Right? So this is how your profile should look like. So we know the initial value here, right? So TC is this. You start at 25. TH is 120. So as you move in the Z direction, heat exchange happens. Your hot fluid temperature goes down. Your cold fluid temperature increases, right? So this is how you get the profile when you have a co-current flow, right? Now you can beautify this graph. As of now, I'm not doing it. Okay, and then put values in a nice way. You have this reference code with you just to modify the plot, right? But now since this was the initial value problem, so we knew the value at TH and TC at Z equal to 0, right? And then we moved with the ODE solvers, right? It could be any solvers, Euler's, RK4. So ODE-45 works on the Runge-Kutta fourth order matter, right? And you move in the Z direction, okay? So based on the initial value, you can compute the value at Z equal to delta Z. And then based on that, you further move it, at Z equal to Z plus Z0 plus 2 times dz, right? So that way you progress in a forward direction and you get the complete profile of your solution, right? Now when we have a co-current problem, this is how our problem statements change. So instead of having this sort of information, our graphics looks like this, okay? So here what happens, you know that hot fluid is coming from the one direction, cold fluid is coming from the other direction. You know the inlet temperature of hot fluid, so you know TH at Z equal to 0, which is 120. Cold fluid inlet temperature you know, which is coming at Z equal to LZ. So TC at Z equal to LZ you know, which is 25 degrees centigrade. Now instead of having a information on the one point initial value, you have information at two extremes, right? Now if I want to use an ODE initial value problem solver like ODE-45 or ODE-15 or anything else, I need to know the initial value. I need to know the value at both TH and TC at Z equal to 0. But as of now I don't have. I only have value of TH at Z equal to 0, not for the TC, right? So in that case my solver won't work because I don't know the initial value. So this becomes a boundary value problem because you know the values at two extremes, okay? So solution of such problems can be done based on two ways. one is a shooting method and another is a finite difference method. Now, what are these solution strategies? So, shooting method is nothing but it's a solution of boundary value problem based on the initial value problem methodology, right? So here, what you do, you take a guess of an initial condition, okay? Then you shoot. Shoot means integrate the solution with based on your initial guess condition, okay? Right? Based on your initial guess, you employ ordinary initial value problems and solve your entire equation, right? Now, then you estimate the error of a target value at the other boundary, okay? So what does it mean? That I know the value of th at z equal to 0. I assume some value of tc at z equal to 0. I employ an ordinary differential equation initial value problem solver. I compute the profile and then I check what is the value of tc at z equal to lz, right? I know the actual value should be 25. If it's not 25, what is the error? You find out the error with the target value, okay, which is your other boundary value, and based on that you refine your initial guess and repeat the whole process till your error becomes minimum, right? So it's an iterative process. In this iterative process you have to guess the value, based on that you have to reach the other boundary conditions and you have to see how far away you are from that boundary conditions, right? Okay, so based on that error you further modify your initial guess and do the iteration again till your error becomes minimum, okay? So that is a shooting method. Then you have a other finite difference method which solves the ordinary differential equation boundary value problems which are designed for that. So what this method do, they discretize entire domain and approximates the derivative at each discrete points using finite difference method, right? So this converts any ordinary differential equations into large system of algebraic equations and that equations are solved together, right? So as of now I'm not going into details of this methodology, right? Sir has discussed some portion of it and I think other TA also has discussed about the methodology part. So that's why I'm not preferring to go into that methodological aspect, but rather this time we will directly look at the inbuilt solver, which is boundary value problem 4c and 5c. It's like fourth order and fifth order of the solution, right? So these are the two ODE boundary value problem solvers you have present in the Matlab, which you can use. Generally, BVP 4C is a default choice, which is good for the most problem. It's also faster. But if you have a sensitive problem or these stiff ordinary differential equations where you want more higher accuracy, then you can use BVP 5C, right? Now both the way you call both the solvers are same. We will discuss that part also, right? So anyway, implementing both the solver just involves changing command from 4 to 5, right? We will come to that aspect also. So what we will do right now, we will solve this counter current heat exchanger problem considering shooting method as well as this finite difference method, okay? So first let's understand why shooting method exists and what kind of importance it will have. If you already have a finite differential method to solve the boundary value problem, then why to work with a shooting method, okay? And then after that we will further look into the another example of boundary value problems, right? Is anyone there? No. This one. Not this way. So you have double pipe heat exchanger problem, right? Now it's a counter current flow. Now we are looking at solution through ODE-IVP methods. So that is nothing but your shooting method. Okay. So again, all the information will remain same. So your given data is as it is. Just give me a minute. Yeah. So here the information about hot and cold stream or your extended details are as it is, only the inlet conditions have been swapped. Now here in your energy balance equation part, previously what was happening, that when we had a co-current problem, right, we had taken dth by dz as a negative, since as we move in the z direction, in the co-current, the temperature of hot stream was decreasing and cold stream was increasing, right? So that's why cold stream had a positive constant while the hot stream had a negative constant, right? But when you have a counter current flow, right, so hot stream, as it's moving along the z direction, its temperature is decreasing. That's why, like previous case, dh by dz has a negative constant minus ua by mcp, right? Whereas for the cold stream, now the flow is reversed, right? So here at the inlet your temperature is 25. As you move along the negative z direction, okay, your temperature is increasing. So if I look from the z equal to 0, from the point of view from start point, right, at z equal to 0, as I move ahead in the z direction, the cold stream temperature is also decreasing, right? If I look at from left to right, in that case cold stream temperature is increasing as my z is increasing. So that's why here also you will have a negative constant for dtc by dz, which is minus ua divided by mcp, right? So the slight change in the equation becomes that both the temperature gradient are negative considering the positive z direction or positive increment in the z direction, right? So when I code it, when I find the constant for ODEs, so first constant alpha, which is for your dtc by dz, is minus u into area per length divided by your mh into cph, okay? Beta is u into your area per length divided by your mc into cpc, right? ODs to represent our heat exchanger, okay? So that becomes my heat exchanger ODE is equal to, it is a function of z and y, which is alpha times y1 minus y2 divided by beta times y1 minus y2 here y is th comma tc. Okay, so this is your y. Given boundary conditions, so you have at z equal to 0, th 0 you know, which is 120, at z equal to l you know tcl, which is 25. So we will employ solution via shooting method, right? So what we have to do here, we have to assume the value of tc at z equal to 0. Okay, so let me take a guess value of tc. Okay, so let's say I consider the value of 35. Right, I don't know what will be the exact value. I'm guessing that the 10 degree centigrade temperature increase is observed. I'm assuming that, so that's why the I'm assuming the guess value of tc is equal to 35. Therefore my initial condition becomes y guess is equal to, so previously it was th in, right, by tc in, but this time this becomes guess value of tc. Okay, calling ODE-IVP solvers to solve this problem. Okay, so what I will do, I will call one solver z and y. This becomes my ODE45, my function which is heat exchanger ODE. You have to provide a z span, right? So z span here, let me create it. Z span can be from 0 to L, right? And your y guess, right? Once you do that, you have to take out the information about the tc. Okay, so tc out, actually it should be so now here we have assumed the value of tc. This is at z equal to 0, right? Assume tc 0 is equal to 35. Check the computed value of tc at z equal to L. So that will be your tc in calculated. This becomes my end variable, and the second column will represent the tc value, right? So find the error in estimating the temperature. So your error becomes tc in minus TC, okay, calculated minus TC, this becomes your difference, right? Let's save it and run it. Let me print it also, I forgot to print value. So display error in TC in computation by first iteration is you display your error so you are getting an error of 0.7667, right? This is actually fairly close if you consider it, because the guess value that I have provided was fairly close. If I select the value of 40 and run it, then you can see you are deviating much higher compared to your 25 value, right? So deviation of 6.30099 degree centigrade is there, right? So now what is the next step when I am using the shooting method? So in shooting method, first you guess the initial condition, you integrate your solution based on this initial guess we did, then estimate the error on the target value. We estimated that. Now you have to do iteration to refine your initial guess based on your error, right? So refining the initial guess based on the error. So here again what I have to do, I have to update the guess value, which is this guess value TC. What I will do, whatever error I am getting, so from the previous value I will subtract that error, right, to understand. So this is a positive deviation, right? So here my error is TC in calculated minus TC in which should be there, right? So I am getting a positive deviation, that means I am overestimating. So it could be that my initial guess value is provided at the higher value, right? So that's why I am overestimating. So that's why I will reduce the guess value TC by subtracting the error. Now here in this problem, this temperature change along with the z direction has a linear dependency, right? So from your ordinary differential equation you can see this involves the first order relation with the initial value, okay? So that's why subtracting the error in the guess value becomes a good assumption, right? But let's say if you have some sensitive case or the ordinary differential equations which involves the power, so in that case you can include some sensitivity constant or some factor which kind of mimics your system's behavior, right, in order to minimize that error or in order to update the guess value. So here the linear operation works. Let's say if you have some power relation, then you can update the new guess value based on the error square or error some logarithmic part of the error, right? So that will depend upon what kind of equations you have. So you have to focus on your ordinary differential equation, its behavior also, when you are updating your guess value for the further iteration, right? So now this is a simple example. So adding this part should work, right? Once you have this ready, the new guess value, what you can do is again calling the ODE solvers, right? So I will have this value, and let me copy paste this part. So after finding the solution with respect to new guess value, I have to update the guess value also. Y guess is equal to th in comma guess value tc, right? And run this part, right? So first time your error was 6.3099. Second time your error became 0.6854, right? Now if you want to further reduce this error, you can do same iteration again. So what we will do, we will again refine the initial guess, right? And this time becomes third iteration and see. So in the third iteration your error becomes 0.0745, right? So your TC calculated here, it is coming as 25.074, which is fairly close to 25, right? So maybe in this 3 iteration I can be done with it, right? Right now I have used the manual portion to update the value. You can create a loop, right? So you can create a while loop where till your error is within the some tolerance limit, you are updating the guess value and doing the iteration, right? Previously we have done it, we have learned about the while loop, right? So the while loop will be perfect in such scenario where you are considering error as a target. Once the error becomes less than your tolerance, then only your while loop will stop, right? Else it will keep doing iteration based on your estimated error. So you can do that. Now once we have this, once we know that error is within the limit, okay, once the error is within the tolerance, compute the data, okay, then it becomes a data computation part. So my TC becomes my y, my th becomes y, all row first column, your z is already there. Now you can plot it, plot z versus th. Let me give this time, give it a red color. Plot z versus tc, we will give it a blue color. I will have, let's say, line width is equal to 3, x label is t degree c, right? Y label becomes your z this much meter, your legends are t underscore h comma t underscore c, okay, and run it. What happened? Oh, right. So this is how your plot will look like. So your inlet temperature for hot stream, which is 120, inlet temperature for cold stream, which is 25 on the other side, right? So at z equal to Lz, and it's increasing as you are moving in the negative z direction. Hot fluid temperature is decreasing as you are moving in the positive z direction, and this is how you get the counter current profile. Right. So this was the solution based on the shooting method, right? So in shooting method, what we have done, we have used ODE initial value problem solvers only, but we have provided the guess value of your variable at the start. Based on that, we employ the initial value problem solvers, you compute the values, you find the error of the guess variables at the other boundary, you find the error with the actual value it should be, right, based on the boundary condition, and based on that error you again update your guess value and repeat the iteration till your error becomes minimum, right? That way you will solve the problem through initial value problem solvers only. Now we will see the actual finite differential methods which are developed for boundary value problems also, right? So the question is then why this shooting method is being used when we have already boundary value problems solver already present. So sometimes when your system is smaller, the difference between shooting method and using BVP equations does not lead to any much difference, right? But let's say when you have a complex system and the boundary value problems does discretization between multiple points, right? So there is computations of values at multiple data points. So if your system is much bigger, you have many variables. In that case, your solution through the boundary value equations will involve multiple calculations, right? So in that cases, your system might become complex. You might get a slower solutions. A slower solution in the sense the rate of computational power will go down. So in such cases, if your system gives you a good result through the shooting method, then you can employ that part, right? Now let's look at the boundary value problem solvers. So in the Matlab, you have this BVP 4C and BVP 5C, which are ODE boundary value problem solvers that employs finite difference method that discretize the domain and approximates the derivative at each discrete point through the finite difference method, right? So it converts your ordinary differential equation into large algebraic equations, okay? So your simple system is converted into multiple large algebraic equation combinations. So now you can understand when you have so many equations, if your system is much bigger, much more complex problems or complex variables, in that cases your algebraic equations will be even higher, right? In that case, you might get a slower speed for your computation. So in such cases, your shooting method might work where you will get a faster solution, okay? But again, the accuracy of shooting method works on what the initial guess you can provide and how you can update the initial guess based on the error estimation, right? So this problem was much simpler. If you remember, like initially I had kept the value of 35. In that case, error was even low, 0.076 something, right? When I changed the value to 40, I had to go to 3 iterations. If I had kept the value of 35, I might have ended up solution within the 2 iterations, right? So your initial guess in the shooting method becomes an important aspect. Then second becomes how you are updating your guess for the further iteration based on your error estimation. Again, here the problem was that I have a linear relationship with the variables, right? So dt by dz was varying linearly with the tc and th. So in that case, I just simply added the error in your guess value. But sometimes when you have a different equations, you might have to do some sensitivity analysis and decide what will be the updated value, updated guess value based on your errors, okay? Now let's move ahead with the BVP part. So in boundary value problem, the Matlab has BVP 4C solvers, right? Just give me a minute. So this is the documentation part for the BVP 4C solver. Let it load first. Yeah, right. So this is the general formula when you call a BVP 4C solver, that you have to provide an ordinary differential function, you have to provide boundary condition function, and solution in it, right? So what does this mean? Here your initial solution gas is provided by solution init command, right? Your boundary conditions are provided by this BC function. Your differential equations are provided through ODE functions, right? Now to create this initial solution, you have been recommended to use BVP init function, which creates the initial gas solution, right? So what does exactly it do is that, let's say you have this differential equation, right? Now you have two boundary conditions given, one by equal one by value at 0 point and one by value at pi by 2 point, right? You have this two differential equations, so this becomes your boundary value functions, right? Then the boundary value conditions, you create a function for that also, okay? So you have created function. Now you know the value, so ya 0. So in the boundary condition function, you have to provide a function such that when your conditions is satisfied, that function value becomes 0, right? So write a function that codes the boundary condition in the form of any function which is equal to 0. So let's say you know the y0 is equal to 0, right? So y0 minus 0 becomes your function. In the second part, you know the y value at pi by 2, okay? So y pi by 2 is equal to 2. So y pi by 2 minus 2 becomes 0. So this becomes your equation, right? Now let's say your boundary is from 0 to pi by 2. So 0 is your one limit, so that's why it's called ya, and the second limit is pi by 2, that's why it's yb, okay? So when you create the initial gas, so for the initial gas you have to use BVP init function, which creates this initial gas. How? So BVP init function, in BVP init function you have to provide the value of x and x initial gas. Based on that, what it will do, it creates an initial gas solution for boundary value problems, right? How does it do that? I think there was a better description for this. Maybe here it was a better description. Help BVP init, right? Yeah. So BVP init forms an initial gas for a solver. So let's say you have provided the value of your independent variable span, your initial gas. So what it will do, you need the value at the extreme point, which is x equal to x start point and x end point. Let's call it as a interval a and b. So this function will return the value at x equal to a and b. So it will return the your y init value for x equal to a point and x equal to b point, right? Now your y init can be multiple functions, so you can have one variable y init, you can have two variable y init. In any case, what it will do, let's say you have a y init as a two variable, okay? So it will provide the both variable values at x equal to a, which is the start point, and it will provide the y init value at other two at x equal to b, which is the extreme point, right? So you get the two extreme values to which is being called, which is then used in your solvers BVP4C to compute the properties, right? Now again, I'm not going into the detailed methodological part this time for this solvers. Maybe somewhere in the next class or based on the requirement we will look at, right? So essentially what it does is your system is discretized in many linear algebraic equations, and then you solve that linear algebraic equations to satisfy your boundary value conditions, right? So that is your whole objective, right? So let's try to solve our same double pipe heat exchanger problem, the counter current problem, with boundary value solvers available in the Matlab. Double pipe heat exchanger problem. You have a counter current flow. Now solution using inbuilt Matlab ODE boundary value problem solvers. Okay. Right. So this information anyway remains same. My hot stream data, cold stream data, heat exchanger property, and the constant in my equation still remain same. Okay, same as the previous portion part. Now I have to create an ODEs to represent our heat exchanger, right? So I am calling it heat exchanger ODEs, which is a function of your Z and Y. So alpha times your Y1 minus Y2 beta times Y1 minus Y2. So this one is for dTh by dz and this one represents dTc by dz, right? Now what else we need in the boundary value problem solvers? We need ODE functions we have defined. Now we need the boundary condition functions. Okay, so creating functions to represent boundary conditions. Okay, such that g of your function is equal to 0, or g of y, in this case let me call it g of y is equal to 0, right? So what are my boundary condition? My boundary condition, first condition is that my th at z equal to 0 is given as 120. My second boundary condition is Tc at z equal to L is given as 25, right? So I will create boundary condition function, again it will be part of z and y. We will write it as y a1 no, you will need actually two values. You don't have to provide z value, but here, so in the boundary condition plot you need the function values. So my function is g of y, right? So you need the y value at 2 points, right? At y y at z equal to 0 and y at z equal to L, right? So this function is defined with variable values at two extremes a comma b, right? So you need the function value at ya, function value at yb. Now ya is the, let's say, initial value, right? So we know the th value at t equal to 0. So ya1 minus 120 should be 0. Then my yb, second value from yb, that will represent my tc at z equal to l, should be 0, right? So this represents your boundary condition 1, and this part represents your boundary condition 2. Okay, now this is done. We have to create an initial guess for the solution, right? So for that, let me consider th guess value as from my previous experience I know. So let me start with a th guess which is at outlet value, which is around 80. tc guess outlet value I will consider it as 35, right? Now we have to use BVP init part to create this boundary condition between a and b, right? Calling BVP init function to create a boundary condition values. So for that, let's me create one z vector, right? And then y guess value will be BVP init. What I have to provide? I have to provide the z value, and I have to provide the boundary not boundary condition function, but I have to provide the value of y just give me a minute. I had simulated it as solution unit initial guess. Yeah, okay. Initial guess. So I'm just creating it as a function of z, and that will be th guess comma tc guess. Let's call me the initial guess. Okay. Now using BVC solvers. And your BVP solvers works like this way. Your solution becomes BVP4C bracket your ordinary differential equation function, your boundary condition function, so which is like BC func here, then your solution unit, which is y guess. Okay, now let me just run this portion and see how well I have coded it. So when I'm doing this, I'm getting some values. It's running without giving an error. So first let's check how well I have coded it. So my solution of the BVP4C lies in the sol part. So if I look at the sol here, it has created this structural field where I am getting the value of x, y and yp. My x value represents the discretization of z from z equal to 0 to 50, right? So I have, sorry, z equal to 10 in a 50 parts, because I had discretized my z into lean space, which included 50 points, and my best by guess also included the 50 points. Now then what else? My solution also includes y part, which is a solution, right? So you can see y1 and y2. y1 represents your th. At z equal to 0, your th should be 120. So is it there, right? Then as you move ahead in the z direction, your th is going down, and at the end y2 at z equal to l, z equal to l, you should get the second boundary condition, which is TCL is equal to 25. That is also being satisfied. Okay. This YP I think is in between part. So there are other informations also. The YP part is, I think, the discretization that has been done for the iteration. Okay. Then there is the statistic, how many mesh point has been created, how many ODE evaluation. So this is number of ODE evaluation. So you have been done 397 ODE evaluation, right? You can further look into the option part of BVE4P to understand what this all option means, right? That is also done. Another part we had used was a BVP init to create the y guess value. So if you look at the y guess value, that is also the structure file. It includes x discretization, which is actually discretization of z, right? Then it includes the y discretization. Now what this function did, BVP init, we provided the discretization in the z, and we asked to find the initial guess value for all this z discretization part. Okay, so here we called a function initial guess. Okay, so for every z value, this initial guess function created th guess and tc guess as a input value, right? So in that, what happened, that my initial guess was taken as 80, 35 for z equal to 0 value, z equal to delta lz, this value was taken, z is equal to 2 times delta lz, this value. So every time I am taking the same value, because as of now I don't know the variation, right? So that's why I am taking the same value, right? Now here actually what I have done is, I should have provided the better values, right? Because at z equal to lz, I know that th should be lz, z equal to 0, I know the value of th should be 120. At z equal to lz, I know the value of tc should be 25, right? So instead of 80 and 35, I could provide the value of 120 and 25. This way my initial guess becomes much closer to the actual value for th and tc, right? Now, so what this does, this y guess creates the discrete value of y for every value of x, and out of which what information is being used, the initial information, which is this ya, and the final information at second boundary, which is your yb. Okay, this two information is then being used in your boundary condition function, which includes ya and yb, where you provide your boundary conditions equation based on the value of at two extreme points, right? So here I know that th minus 120 should be 0, and for yb tc minus 25 should be 0. So if I provide the guess value much closer to the actual boundary condition, it will solve it much faster also, right? So if you want to see that, let's just focus on this part, only the solution part, right? Here the information statistic is given, that maximum number of ODE evaluation were 397, right? And NBC evaluation, number of boundary condition evaluation were 10. Okay, so ordinary function evaluated around 397, close to 400, and number of boundary condition evaluated were 10, right? So let's see, when I change it and provide much closer value, does it change or not? And if you run it, it has already run. Okay, then look at the solution part and the statistic. it's still same, so probably the number of iteration required were same. Oh, yeah. Let me check first. It should help you in some way. Help BVP force. What are the other parameters that you can provide? Okay, you have to just put the this option function like OPTS, then it should give the statistic data, right? So let me put it here. Ah. What are these options? Okay, just let's do statistics on and then see how it works. I think this were the other option are specific to that example that they have discussed. If I just put this, then let me see what is happening. Okay, so with the initial guess value, then I just had to change this. Like you provide the option, which is a BVP set where you provide the statistics as on. So you are getting that maximum. No, this is the same information, so it doesn't matter. No, this information was anyway printed here. Same information has been printed. No, there is no point of doing this, but I think this will help. Like the closer your guess value to your initial part, it should help you. Okay, let's say as of now we are just keeping it away. Now once you know the value, so you have computed the solution. Now your solution now your solution contains discretization of x and discretization of y along the z, right? So sol dot y will give you the y vector, sol dot x will give you the z vector, right? So I can call the solution, you can extract the data by doing y is equal to sol dot y, right? Anyway your z is already known, sol dot z, sorry, sol dot x, okay? Your tc becomes, or your tc is y all row second this thing, and then your th becomes y all row your first column, okay? You can plot them like the previous part, z versus th, comma z, comma z versus tc, comma blue, line width is equal to 2. Right? Plot it. Let the data extraction has been changed, like it's a row vector, right? So I have to change it. And run it. So this is how your graph will look like, right? So this is your th, this is your tc, and the conditions are similar to what you have observed with your this ODE-BVP through the shooting method, right? So same way you can use either your boundary value functions or your initial value problem solvers by providing some guess value to solve your boundary condition problem. So you have two options, right? So we saw one option through shooting method, another through boundary value functions to solve the ordinary differential problems, right? So this two approach can be used to solve ODE boundary value problems, right? Now you can do further modification again in the plot part. Here I haven't done it. You can just customize it to represent graph more neatly like this, right? You can extract out the data and stuff. Again, the reference code for the proper reference code are provided here, and the in-class code that we are doing right now is also provided here, okay? So the class portion code is just to make you understand how the coding part works, and the reference code are for further enhancement and modification for the better data representation part, okay? Now once this problem is done, we move ahead with the another example of boundary value problem, that is reaction in the heterogeneous catalytic palette, right? So for that example, let's look at the problem statement first. How much time we have? Yeah, we have plenty of time. Okay. So in this problem, what has been given to us is a catalytic palette with reaction diffusion. So a first order reaction A giving B is occurring inside a spherical catalytic palette. A reactant A diffuses into the palette from a surface while simultaneously it's being consumed in the reaction. Okay, so this sets up the concentration gradient inside the palette, right? So at the surface you will have a maximum concentration, and as the reactant is diffusing inside the palette, your concentration will go down. As well as it's since it's being reacted also, so with time you won't reach exactly a steady state, because with time it's also being consumed, right? So now when you want to solve such catalytic reactions problem, right? So in that case, apart from your normal reaction mass balance, you have diffusion, you have to also encounter diffusion of your reactant inside such palette, right? So if you remember and recall your Fick's second law, which gives you the change in the change in the rate of your concentration. Okay, so change in the your concentration, right? So dc by dt. So dc by dt is given as diffusion into your del square c by del x square, that is in your normal Cartesian coordinate. But when you convert your problem for spherical coordinate, or you look for your problem in the spheres, you get dc by dt, which is your change in the concentration with time, is equal to d by r square. D is your diffusivity of your gas into your palette per r square into d by differentiation of r square dc by dr with respect to r, right? Now here the change part, the rate of change of your component with respect to time, it can also be related with your reaction part, right? Since the component is also taking part in the reaction, so your dc by dt will become your minus Ra. Dc by dt is your minus Ra, which is k into c, right? So this is how your equation looks like. Now here, what are your boundary conditions? So if you consider this palette scenario, let's say this is your spherical palette. Okay, your component A is here, right? And it's diffusing in this direction inside a core, right? So in this surrounding part here, you will have a maximum concentration of A, right? So if you look at the surface point here or anywhere on the surface, so at R equal to capital R, at your surface of the palette, your concentration will be maximum, right? So C is given as CS, whatever notation you use. It's like I am using S as to represent the maximum concentration, surface concentration, right? And at the core of the reactor, since here your reactant is moving from a surface to inside part, you will observe the concentration gradient, right? So if I look at here, this is my R and this is my C. Sorry. This is my C. So let's say initially you have a maximum concentration, as you move along with the palette, you might have some sort of a this profile, right? Okay, so at inside the core of your reactor, your concentration will be minimum, but we don't know the exact value. But from a profile, you can say at the core at R equal to 0, the rate of change of your reactant with respect to R will become 0, right? Because this is the core part. So beyond this core, there won't be any change in the concentration part. Since there is no change in the concentration beyond the core, your gradient of dc by dr at R equal to 0 becomes 0, right? So this becomes your ordinary differential equation. This is a differential equation, right, with a higher order. And you have two boundary conditions. One is at r equal to 0, another is at r equal to r, which is the surface part, right? So what are these your boundary conditions? So one is that your surface concentration your surface concentration is constant, which is r equal to r, and your core, there won't be any gradient in the concentration. There your core will be at a constant value of dc by dr, right? So now when you modify this equation, so what I have done, instead of dealing with the concentration and the radius part, we have converted it into the dimensionless number, where your y represents the concentration ratio at a given instant r. So your y is equal to c by cs. Your x is a radius ratio, so your radius divided by the maximum pellet radius, capital R, right? And when you discretize it and solve the above problem, so and simplify it, you get this following the ordinary differential equation in terms of the dimensionless number y and x, right? Where this phi represents your Thiele modulus. So your Thiele modulus is, if you recall your reaction engineering, it provides the ratio of reaction rate to the diffusion rate, right? So here you have rate component and the diffusivity component, right? So your Thiele modulus represents the ratio of reaction rate to diffusion rate. So your ordinary differential equation to represent the reaction into the catalytic pellet looks like this. Okay. Now here what have been asked to us, that if you have a radius r given as 0.01 meter, Thiele modulus S2, solve the concentration profile and then calculate the effectiveness factor. Now effectiveness factor is a ratio of actual reaction rate in the pellet to the rate if we consider that entire pellet was at a concentration CH, right? So this is given by this equation. Just recall your reaction engineering fundamentals, and then you will end up with this equation, right? If you are not able to recall it right now or understand it, just go back to your books and just solve it. You will understand it, right? So this was the one part. Now let's try to code it in Matlab. So this is catalytic pellet with diffusion reaction. Okay. So not action, it's R. Diffusion reaction, right? So what information we have right now? We know the Thiele modulus value, we know the pellet radius, right? So first start with the given information. Your phi is given as 2, which is your Thiele modulus. Then your R is given as 0.01 this much meter, right? This is your radius of pellet in meter. Now first creating a ODE function to represent our system, right? So here what will be my ODE function? So as of now you can see I only have one equation, right? But this equation involves first order derivative of y and second order derivative also, right? So this dy by dx is first order derivative and del square y by del x square is second order derivative, right? So what we will do, we will create a function that represents both first and second order derivative of y, which is your c by cs, with respect to x, which is your r by capital R, right? So my reaction ODEs becomes function of x comma y, where so this becomes, x will represent my differential component, the independent variable, right? And y will include dy by dx. Okay, so let me call this as y1 will include dy by dx. Then my y2, second component of y, will include d square y by dx square, right, is equal to, you can also write it as dy1 by dx. Okay, so my y1 will represent the first derivative, y2 will represent the second derivative. Okay, you can also write it in a better way. And this is your second. Yeah. So this is nothing but y1, right? My ODE will include y1 is just dy by dx, so I'm calling it as just y1. Then my y2 will be this function del square y by del x square, that becomes Thiel modulus square into y minus 2 by x del y by del x, right? So phi square, just a minute, y1 into y2 no, my mistake here, sorry. Y1 should only represent the y value, not the derivative part. Okay, so y1 represents your concentration, and y2 represents your dy by dx, right, which is your second derivative. So you can also write it as y2 is this dy by dx. Okay, sorry. So this is your first derivative. So this just defining the my variable function properly, right? So now my ODE will include, so first part of my ODE is first differentiation, right? So my ODE create a function that represents both the first and second order derivative of y with respect to x, right? So the first row of ODE represents my first order derivative, so that is my y2, and the second includes the second order derivative, that includes phi square y1 minus 2 by x y2, right? So phi square y1 minus 2 by x into y2, right? So this is how it should look like. Yes. One more thing here, since my x will be in terms of matrix, it will be in terms of matrix, right? In terms of vector. So that's why I am putting a dot product here. Okay. So this you have created the ODE, creating a boundary value functions now. So your boundary value functions includes this part. So you have two boundary conditions, that differentiation of c with respect to r is 0, and at second is your constant value, right? So first boundary condition 1 says that your dc by dx is equal to 0, right? Or dy by dx is equal to 0. Your boundary condition 2 says that your c is equal to cs at r is equal to 1. That means your y will be 1 at x equal to 1, right? So y equal to 1 at x equal to 1, and here this is at x equal to 0, right? So let me define boundary condition function that will be also function of, this will include ya and yb part, right? Like previous case, that we need boundary condition at as x equal to 0 represented by ya, we need boundary condition value x equal to 1, but that will be represented at yb, right? What does it say? At boundary condition 1 x equal to 0, which includes ya, my first order derivative is 0, and first order derivative is represented by y2, so right, so ya comma 2 is equal to 0, right? So I don't have to write anything here. Then my second condition says at x equal to 1, which is represented by yb, my y value is 1, so y value is represented by y1, so yb comma 1 minus 1, so this will be equal to 0, right? So this is my boundary condition, right? This is boundary condition 1, and this one is boundary condition 2. Okay, this is done. Now next thing is to define the initial guess values, right? So first I have to discretize my x. Okay, I can do this by linspace, Now here ideally I should start with 0 to r, and let's say I'm considering 50 data points in between. But here one thing is that in your equation you have this 2 by x component, right? So if I will have the value of 0, 2 by 0 is infinity, right? So in that case I will get an error in the solution part because I'm encountering the infinity. So rather than having the value of 0, I'm putting a very small value, let's say 0.00 10 to the power minus 6, right? X equal to 0 is avoided to avoid in INF in the code, right? So this is an important aspect. This you remember, that instead of starting the value at exactly 0, I am starting the value at 10 to the power minus 6. Why? Because my ODE contains inverse of x, right? So when I will have x equal to 0, you will get the infinity, which will cause error in your solutions, right? You have created the value of x. Now previously what we did, we use BVP init to find the initial condition, right? So help BVP init, right? It creates the initial guess for BV. So you have to create the x data and the y data, right? Now to create the y data, guess value for y. So I have to assume, right? So let's assume a parabolic relation of y with r. So that means my y1 guess can become 1 minus, let's say, so it's a parabolic relation, right? So 1 minus with respect to r. So what was it? I think I created x mesh into dot square, 1 minus x mesh into square, considering the 80% conversion. So 1 minus, let's say, x dot square. So here what I'm considering, let's consider the guess value goes from 0.8 at the center to 1 at the surface, right? So that's why I'm creating 1 minus 0.82 x mesh square to represent the parabolic relation, right? You can select the any value which kind of represents the your system behavior, right? As of now I am selecting this 0.8, going with the previous information that I have. Okay, now your y2 value, y2 guess is nothing but y2 guess. Y2 is your differentiation of y1, right? So y2 is dy by dx. So differentiation of this quantity will give you minus 2 times x square, right? So that becomes minus 2 into 1.8 x mesh, right? So minus 2 1 minus 0.8 into x. Okay. So these are your two guess values. Then what you can do is you can use x mesh. I think I can use them directly. I don't have to use interpolator. Yes. Okay. So you have created the guess value. This is for y1, this is for y2. I can use initial, I can create initial guess function as BVP4C as a combination, not BVP4C, BVP init, right? BVP init, I have to provide the value of x, I have to provide the y init parameter. Now y guess, I can combine these two variables, y1 guess comma y2 guess, give it as y guess, right? Once that is done, now calling BVP functions to solve the problem. So my solution will be BVP4C my ordinary function, which is reaction ODE, comma my boundary condition function, comma your initial guess. Right? Let's run it and see whether I'm getting some value or I'm getting an error. There is some error, invalid use of operator. Why? It should be here first. Initial guess function must be a vector, so here it should be on space. Error in calling BVP, the derivative function OD function should return a column vector of length 100. This is a row vector, this is also row vector. Here I am creating a row vector. Yeah. Initial guess at the rate all value of your x. Now I think it should work. Oh yeah. So sorry. Essentially, here the problem comes in defining the initial guess function part. So basically, what we have done, we have computed, you have discretized x into various 50 mesh bins, right? And then we are assuming the value of y1 and y2 along this bin. But when I'm calling the initial guess, I have to say that corresponding to x, what should be the value of y1 and y2 from this y guess matrix, right? So that's why I have to use interpolate command, which will provide me the value of y1 and y2 at a particularly x part, right? So that's why this interpolator command is there. I forgot that part. So let's say we use interpolate. I have to provide the y1 guess. I have to provide the x mesh, y1 guess and x. So x value, y1 guess and small x. it should work. Yeah, now it's working, right? So basically what I was doing, I was just directly calling y1 and y2 guess, but BVP init asks that for each value of x there should be one value, so I have to provide that. So that's why I have created this y guess function, which interpolates for corresponding x value what is the value of y1 and y2 based on the matrix data provided. Once that value is that, it is taken by the initial guess function, right? So your init get function, which is this, you create the ya and yb data here, right? So that has been created, and this is your solution. Sol is this, where you get the value of ya and yb. Now let's try to plot this value and see what kind of profile we are getting. So your y becomes sol.y I need the value of y1 because that represents my concentration profile, right? So concentration small y is equal to y comma all first row comma all column. Then I can do plot my x versus small y. What happened? Y is equal to 12. Only the 12 part discretization happened. Here my mistake, it should be 1, x equal to 0 is avoided. Yeah, I had kept the value of r, but this is the x vector, right? So it should be x equal to 1, and then still there is some error. Solution by let me interpolate the data. So I will have x solve, y solve, and that's it. Yeah. So this is how my profile will look like. It's a parabolic profile, right? So the slope at at r equal to 0 becomes 0, right? So my dy by dx equals 0, and my y at x equal to 1 becomes maximum value. It's cs, right? So this is true, correct? So this is how your solution actually looks like. Now here line space we want. So this d will actually discretize the value for the various points in between from the solution side, just to create more data points, right? You can represent it in this fashion. Here So here what I have done, I am representing the data point, same data point, but just the representation way is different. And this in between round dot points are the solution points from the BV4C solution, right? So the BV solution gives you the 12 discrete points in your solution solve, right? Here 13 in this case, and then this 13 discrete point you further convert it through dval function into discretized point of 100 to get a much smoother data plot, right? So if you recall in the even search class also, you have done it that you have in between data points, and to create a smooth curve between this data point you use dval command, which differentially evaluates in between data points, right? So that you can do, and this is how your graph will look like. This way you can see it looks more like a parabolic profile, and you can understand here that yeah, exactly when we are approaching at r equal to 0, my slope is becoming 0, and its maximum the maximum value I have for y equal to 1, which is my c is equal to cs, is at r equal to capital R, or in this case x equal to 1, right? What else has been asked to us is that we have been asked to solve the value. So we have been asked to find the effectiveness factor, and effectiveness factor is calculated as x equal to 1, right, which is this 3 by 5 square dy by dx at x equal to 1. So it's a first derivative value at x equal to 1, which is the end point, right? So I can take out that data, right? Just so you can write to find the effectiveness factor, you find dy by dx you compute. So take out your solution, capital Y solve, second row your end data point, okay, then your effectiveness becomes 3 divided by phi square into your dy by dx and you can represent it at display for given phi equal to 2, the effectiveness factor is, then display your effectiveness and this. So you are getting the value of 0.806. If I see the previous code also, yeah, I think that means it's the same value, right? So this way you can also compute the reaction engineering problems, heterogeneous catalytic problem, where you generally have the boundary conditions given, and based on that you have to solve your ordinary differential equations, right? Now here you can further modify this problem by looking at what will happen when you vary the Thiele modulus to different values, and then you can see, so Thiele modulus represents your reaction rate to the diffusion rate, right? So you can vary it and see what which effect dominates more, whether it's a reaction or whether it's a diffusion part, right? So that could be the sensitivity analysis part that you can do, right? So this is it for today's class. I will stop here. If you have any doubt, do let me know, then I will try to cover it into the next lecture part. Okay, so I'm stopping the recording. Thank you for joining.